I never wanted to do this, like this job. Maybe there was a paradigm shift somewhere that I missed. But I wanted to be a football player. And I got injured. I came very close. I got injured. I have to move on. I failed at that. So then I became an engineer, which I didn't like very much. I wasn't very good at it. So I moved on again. Failed at that. Then I became a teacher. Wasn't particularly good at that either. So had to move on. And here I was at 30 years old, having not succeeded at playing football, not an engineer, not working in the private industry, and not a good teacher. So I decided to do what any other sane, reasonable person would do. I became an academic. And I'm still waiting for some kind of productiveness to happen, but I hope that happens. Okay, so what I'm going to share with you is the last 10 years of my work, the work that I've done in Singapore schools and teachers around a mathematical intervention called productive failure. Although the work is in the domain of mathematics, it sort of applies to other domains as well, right? So, well, what does this happen? You know, I keep messing it up because it's the left one that I should be pressing. All right, okay. So every conversation with the teachers and the school leaders that I start with is first an understanding of the problem. As Professor Zhao just said, you know, there's a lot of teaching is about teaching. You're telling, you're an expert, you want to share. There's a lot of direct instruction. I come in and I tell you. So what is the problem? Why do we need to change it? So this conversation has to start with, okay, so what's the problem? Now the problem is one of noticing and seeing. So imagine, for example, you're watching a very engaging movie, very entertaining movie, and sitting next to you is an acclaimed director. Okay, you watched the movie, you had fun, you liked it, you come out, and if I were to ask you the question, did you and the director watch the same movie? Did you see what the director saw? Chances are you did not, and that's what decades of research and experts versus novices suggest. If you're an expert, given the same stimulus, same piece of information, what you will see is very different from what a novice sees. So you can have the most wonderful presentation, a logically structured explanation. What the novice sees is very different from what you're seeing. In fact, the novice is more likely to see superficial features. And you as an expert are seeing beauty and dance in that equation, you know. It's very different. So the first job of teaching, therefore, is not to assume that students can see, no matter how good your presentation is, right? Because novices see different things from expert. Therefore, the first job of teaching then becomes it's not to teach, it's to prepare students to see. Give them the proverbial eyes to see what you want them to show. You can still show them. I know it feels good to show things, you know, share knowledge and everything, but you've got to prepare the students to see. Now, if as teachers we begin to understand that this is the problem of cognition and that we need to then change it, that's the first step. That's the first shared understanding of the problem that we develop. Next up, well, before we jump to the solution, or one of the solutions, we've got to think about what are our shared goals. So there are schools and there are teachers. I come from a system that is very test-centric, a lot of standardized tests, and that determine your life pathways. So I ask teachers, okay, so what are your goals? Do you want to develop mathematical knowledge that is good enough for you to do well on these exams? A lot of teachers would say yes. It's a moral and ethical responsibility because lives depend upon it. Or say, okay, you want A plus you want also students to understand because you can do well on these tests without understanding very well. The teacher say, yeah, I want that too. That's good. Then I say, well, do you want A plus B plus, sorry, it's mathematical, the ability to transfer what you're learning to new situations. Now, transfer is something you can't test in a standardized test. Okay? But that's sort of the idea, right? What's the point of learning if you can't transfer it to solve novel problems? Right? So teachers say, yeah, okay, maybe that too. And I say, okay, but what about, all this is knowledge about mathematics. What about mathematical thinking and reasoning and thinking and being like a mathematician? Don't you want that as well? They said, yeah, I start to lose some people here when I speak to some of the schools. And they say, okay, but there's more. Do you want all of that plus a lot of the 21st century skills like collaboration, inventive thinking, creativity, persistence and resilience and so on and so forth? And by the time I'm done here, about 10% of the people are still with me. And those are the 10% of the people I work with. Because unless you have a shared understanding of the problem, a shared set of goals, and I'm very clear with my teachers that if you just want A or B, you don't need to work with us. There's no need to intervene here. It's when we believe that there's more to achieve and aim for, that's when we need to rethink how we teach. Okay, so shared understanding of the problem, shared set of goals. Let's move on to what a solution might look like. And it turns out failure is a very good way to achieve that. So let me give you an example. If you were in my talk yesterday, just go through it as though, just ignore everything that I'm going to say. All right, for the rest of you, even if you're not math teachers, this is an interesting exercise in some imagination. Because this is for novices who have not learned the concept that this activity targets. So here are 3 football players. Okay, here are a number of goals they've scored each year. And the question for students is, who's the most consistent player? These are grade 8 or 9 students, 14, 15-year-old students. They've not learned the concept, the underlying concept yet, which is standard deviation or variance. Okay, they've not learned it yet, but they're first asked to do this. What do you think kids would do? This is not a rhetorical question. just some ideas, just shoot out some ideas. What do you think kids would do? Sorry? Right, so who has the most goals, maybe? Okay, totals. Averages, very intuitive. What else? I really want to hear from non-math people, actually. Similarity, how similar they are. Okay. Graphs? Gaps between each time. Okay, that's very interesting. What else? Minimum to maximum. Very good. Okay, let's move. We don't have a lot of time, so I'm just going to show you what they do, and you'll see some of these ideas. Now, reminder, these kids have not learned the math yet to do this. So yes, they do a lot of averages, mean, median, mode. And part of the principled ways of designing these activities is to induce failure through prior knowledge activation, right? So it's failure-based activation. So we've kept some things invariant, so the student says, oh, I used averages, oops, it doesn't work because it's all the same. So I need to think of something else. So they start tallying, and they can qualitatively argue who's more consistent, less consistent. We push them to quantify and be more precise. They draw some dot diagrams. Again, the same thing, quantify, be more precise. Some of them draw these fever curves. They say if it's going up and down a lot, it's more inconsistent. If it's not going up and down so much, it's less consistent. It's more consistent. And we say, okay, these are good ways to get an intuitive feel. None of these solutions are perfect. Can you make them more quantified, more precise? Some of them count how many years above the average, below the average, at the average. And they say, well, let's take a ratio. Consistency is just how many times you were at the average divided by how many times you were away from the average. You don't need to be a math major to understand this. If this ratio is high, it means you're more bunched up. If this ratio is low, you're more spread out. Again, you won't find these solutions in a textbook, but these are just some very intuitive ideas the students are able to generate. They do take maximum minus minimum. The range, again, it's kept invariant so that they have to push on and find out a new solution. They take, so I think this is your solution, they take year-on-year deviation, like a economy or property market, and they add up all the deviations and say the higher the total, the more inconsistent the person is. The total change in the data is a lot. Some of them actually realize that positive and negative changes are cancelling out. So you need to be fair and just take the magnitude. Okay? And these are things that students do. Very rarely do they come up to deviations about the mean. So those of you who are mathematically inclined, you will know that this is the way to start the process. But because they've not learned the concept, they don't reach here yet. But they also do something very interesting from time to time. Now here's a group of students who were asked to quantify their graphs. They said, imagine I could take two ends of the graph and extend it and make it a rope. And if I could somehow calculate the length of that rope, that's a measure of consistency. The longer the rope, the more inconsistent. Yeah? And they've learned Pythagoras' theorem. They've divided this into right angle triangles, for those of you interested. They've calculated this length here. And the idea is, so far, to this date, I've never checked the calculation. Because the real mathematics is not in the calculation. The mathematics here is in the creativity, it's in the play of imagination. That's what gets invoked when you're getting students into these design spaces where they have to create before they learn. Now, this is the activity, this is the kind of a design that helps them, that provides them with the eyes to see what the teacher can then come and consolidate and build on this knowledge. That's when they begin to understand what is critical in what they're learning from you or from the teacher. Okay? And that's what productive failure is about. So you've got mechanisms that are embodied at multiple levels. You've got the cognitive mechanisms going on about noticing and activation. I won't go into the details. You've got affective mechanisms that are embodied. Thus, you're building up situational interest because of this. You're orienting them towards mastery. You're building frustration. Students get frustrated when they do this. Every time they come up with a solution, either it obviously does not work, or the teacher pushes them to improve it. By the end of it, they really want to know, so what is your solution? A lot of teachers, a lot of teaching designs somehow seem to think that making learning easy eases learning, when that is not the case, right? So you've got to build frustration and struggle, and helping students persist through that frustration. That's part of learning as well. There are social mechanisms at play about explaining, elaborating, critical thinking, and working with each other. And finally, there are cultural mechanisms. Now, this is probably the most important set of mechanisms, because here what we're saying is failure. We are normalizing failure. If you're not struggling with something, your chances are you're probably not learning. This is basic learning theory. Okay? Vygotskian notions of zone of proximal development. If it's too easy, you're not learning. If it's too difficult, no chance. But if you're struggling right in that zone, there's a chance that you might be learning. And so we want to make failure as positive. You want to focus on effort and growth, so those mechanisms are part of the cultural milieu that we start to grow in the classroom. And above it all, it's a mathematical culture that you're developing in the classroom. It's not learning about mathematics, it's learning to be like a mathematician, right? And that's part of the shared goals, and that's a culture you want to build. So the unit of change, therefore, then is not a new pedagogy. The unit of change when you want to do this in the classrooms is culture. You've got to change cultures. It's about changing cultures, not changing pedagogies per se. Okay? All right, so I've talked about, so it's a two-phase design. How much time do I have? I have, okay. That means I have fair enough. So it's a two-phase design. So in the first phase, we get students to generate and explore the solutions that they generated. And then the teacher comes in and talks about it. Perhaps this is similar to just in time. You create the time to share with the students. So it's important, right? And like I said, when we design this, we are designing the whole classroom culture, the set of norms and values within which the social participation takes place, within which that cognitive activity is done. So when you're changing, we've got to change multiple levels. The tricky bit here is this takes a longer time scale to achieve than this layer, and this is the shortest time scale. So if you're building any change effort and you're thinking about new activities and methods to teach, you're here. But if you want to change the classroom culture, you've got to persist with it over time. But that is something you already know, right? Okay, so we've done experiments, a lot of experiments in Singapore classrooms, and it's been replicated worldwide. So I'm just going to share very quickly the kinds of evidence that we have, okay? And we've compared it with the direct instruction model, which is basically just the reverse of that, which is the typical way, at least in Singapore, kids are used to being taught. Okay. So what are some of the findings? So as I go through the student findings, I also want to emphasize the kinds of shifts that we start to see in how teachers think about learning. Okay, so I will illustrate that. Okay. One of the first things, one of the very consistent pieces of finding that we have is when you compare on the basic knowledge about mathematics, the basic set of procedures and skills you need to do well in the exams, there is actually no difference between productive failure and direct instruction. Both methods are very good at developing high levels of fluency very quickly. So again, my promise back to the shared goals, that if that's what you want, you don't need to talk to me. Right? That's the goal, you're achieving it already. But if you want better understanding, conceptual understanding and better transfer, yeah, we're seeing very good gains. And the kind of teacher learning that happens is, that we notice is what I call the basic knowledge fallacy. We're used to thinking that, oh, this is basic concepts. Addition, multiplication, subtraction, ratio and proportions, and data analysis. These are very basic things. We can just give it to the students. What's the problem with that? Well, it turns out, from a cognitive standpoint, how you receive or encode that information influences how well you can use it. It's not like a file on the computer. Once you have it, you really have it. No. It's how you encode that process actually influences. Because here we have two groups of people who appear very similar on basic knowledge, but are very different in how they understand it and how well they can use it. So that initial learning trajectory actually matters a lot more. What we also begin to see is the creativity measure in design ability, the ability to develop solutions to novel problems. Direct instruction actually constrains this design ability. When we ask kids who had learned the concept of standard deviation and asked them to solve the same problem in multiple ways, the solutions that they gave us were the formal solutions. They all could solve it. But we said, no, can you think of other ways too? Couldn't go beyond the knowledge. So we used to thinking, or teachers are used to thinking, let me do this basic stuff first, then I can engage students in higher order, creative and inventive thinking. Well, by that time, the sort of boats left the shore already. You've got to attack. So knowledge is not like that commodity. You've got, how you acquire that, how you build that knowledge actually influences how creative you can be. And we've known this from child development psychology for a very long time. Suppose for half of you, your children imagine, it's fun, I show you a toy, and I say, hey, here's how you play with this toy, and I give you the toy, and you play with it, and I observe what you do. To this half, I say, hey, here's a toy, play with it. You see the difference? Here I showed them, and here I just play, and I observe. Who do you think is more inventive? This group, and we know this from research, okay? This group is way more inventive. Concepts, knowledge it's a conceptual toy. Yet we make the same error. You need to prepare. Very good, okay. So that's what I call the creativity fallacy. And teachers start to think, okay, I used to think that creativity and inventiveness can come later, but actually, no. I need to think it from the start. If you build in creative, inventive process while learning new things, chances are those things can be used for further creative, inventive processes. Okay? The other shift that happens, and because in Singapore we have streaming, we are based on this 6th grade exam, primary school leaving examination. Children are divided into different streams depending on how well they do. And every time, so I started my work in a very mainstream average ability school, and I went to the teacher and said, let's do productive failure. And they said, oh, this is really good idea, I believe in it, but it's only good for my best students. Best classes would do it. And I said, oh no, but it would work. We've designed it for it to work with every student. I said, no, you don't know my student. So we carry out the work, we get good results. So I go to another school, which is 1 or 2 standard deviations above this school. And I go to the teacher, look, I've come from this school. I've got great evidence. Would you do this with your students? He says, yeah, that's good. I think it will only work with my best students. Best classes should do it. I said, no. I've come from a school whose best classes are worse than your worst classes. He says, oh, no, Manu. You don't know my students. I said, all right. And then I go to a top-of-the-line school in Singapore. These are really good schools. They are performing a year or 2 ahead of the mainstream schools. And I said, hey, look, I've got evidence from mainstream and slightly above average schools. No, Manu, you don't know my students. It's only for the best classes. The point I'm trying to make is we as teachers have these beliefs about who's able and who's not, and we use those beliefs to systematically afford or deny opportunities to learn. And when you start to see through this work that teachers start to shift, become more humble in terms of what they estimate what people can do, that's when change starts to happen. The early change starts to happen. I think I'm running out of time, maybe? Okay. I'm going to use your time a little bit. Thank you. So other things that teachers learn. I was asked teachers, so would you do this again? this is a very stressful way of teaching because the development runway is longer. So one of the things that teachers always tell me, I don't know about the method, Manu, but having taught this way, I myself learned math better. Now, our teachers in Singapore come from the top third of the graduating cohort. So these are good content experts, top third of the graduating cohort. And these teachers are telling us, having taught productive failure, I now understand the math better. Because when you're working with students' ideas in inventive design processes, your own knowledge is going to be pushed. And that's when they understand the math better. We also focus on pedagogical content knowledge and design knowledge, but it's very hard. At least the experience in Singapore is people are not exposed to, in their training, in their schooling experiences, in inventive and design processes. So you can't ask somebody to suddenly create a culture of invention and generation and exploration if they've never experienced it themselves. And part of the workshop that we'll do later is to see how we build that into the professional development experience. Okay, so that's a very hard shift to take place when it comes to pedagogy. I talked about how teachers underestimate, and this is true for every expert. Experts tend to underestimate what novices can do by virtue of their expertise. And a lot of teachers would tell me, Manu, I don't need so much time to do this. I can teach standard deviation or proportion very quickly. But after they do productive failure, I said, okay, even if you don't do productive failure, if you were to go back and teach this concept, would you take the same amount of time? The answer is no. Because when you understand the concept better, you realize that you've got a lot more to teach. So covering syllabus, like you mentioned, covering 3 or 4 concepts, covering is not teaching. You can cover very fast, but you can't teach. Once you understand the domain, you can't teach very fast. Okay? And finally, scaffolding. We all use the word scaffolding a lot, but at the heart of scaffolding is the idea of failure. If you look at Vygotskian notions, you can't determine the zone of proximal development if you don't have information of what is it that people cannot do. That is information about failure. So if you're designing activities and classroom learning experiences for your students and you don't have information about failure, your chances you're not teaching well. Okay? With that, I think I should stop here, and thank you, and I look forward to the workshop later on.